Welcome back. For the second part of today's course session, we are going to start looking at a topic that goes under the name of random variables and expectations. And as I mentioned earlier, this is the last topic that we will cover in the course before the recap sessions during the last week of the course, which is actually going to span over 2 weeks because of the Easter break in the middle. Before we do that, however, let's entertain ourselves by considering a problem which many of you probably have already seen in some form or another. And that's the so-called birthday problem, or some people call it the birthday paradox. Because like several things in probability theory, they look somewhat paradoxical, or they go against, the answer goes against or sort of our intuition, whatever our intuition might be. Very often our intuitions are wrong anyway. So that's not surprising that math goes against it. Now, the birthday problem is as follows. Suppose you're at a party and you ask yourself, okay, how many people do I need to invite at my party so that the probability that 2 of them have the same birthday is larger than half? Okay, you could try to guess, but you don't want to guess because you don't want to invite too many people. You will need to pay for the drinks and all that stuff. On the other hand, I mean, it's also satisfying to know how you could go about planning your party in a systematic fashion. Well, in order to answer these questions systematically, we typically need to make some assumptions. And here are 2 assumptions that we will make in order to address the answer to this problem using the tools of probability theory. We assume that the birthdays of the people we might invite are independent. That is to say, the birthday of your friend Sigurdur is independent of the birthday of Austa. Moreover, the birthdays are uniformly distributed. That is to say, the probability that a person has a birthday on any given day of the year is the same. Is 1 over the number of days in the year. Now, that's an assumption which is not true actually in real life, but it simplifies our calculations. In real life, I think there are certain times of the year where more people are born. At least this is what you learn when you have kids, and you see there are periods of the year where there are lots of birthdays in a row, and there are periods of the year where nobody seems to be born. Well, nobody, fewer people seem to be born. But anyway, we assume that people are born uniformly throughout the year. Now, to make things simpler, we assume that every year is a leap year, so that we don't need to distinguish leap years from non-leap years. So there are 366 days in a year, and the probability that somebody picked at random is born on any given day is 1 over 366. Okay, so given these assumptions, we want to figure out how many people we need to invite so that the probability that 2 of them share a birthday is greater than half. Okay, so how do we calculate this?
Because there's a person that has a birthday of today or not. So we could like take it.
Actually, so your colleague is saying this could be a Bernoulli thing. It's actually a reasonable thing to say, but it's not quite like that. Let's see why. So first of all, well, let's try to calculate the probability, let's call it P sub n, that n people have all different birthdays. Okay, then we can compute the probability 1 minus P of n that tells us that at least 2 of them actually share the same birthday. Okay, so how do we go about calculating this probability? Well, think about it this way. This is the room where you're holding your birthday party. And you decided to hold it in V101 because we are amongst friends here. But V101 is empty to begin with. There is only you. Okay, you let the people come into the room one after the other, the people you want to invite. Now, the first person comes along, and you want this person to have a birthday different from all of the other guests. Well, the probability that is the only guest so far, assuming that's a man, is the only guest, the probability that he has a birthday different from all of the others is 1, because he's alone. Okay, so the probability that the first guy has a birthday which is different from all of the other guys in the room is 1, because there was nobody in the room before he came. But now we have a guy in the room. Okay, now you want to invite a lady, because you want to match, mix and match anyway, sort of. So you want a suitable gender balance so that it's a fun party. Okay, now the lady comes along. The lady comes along. Now, what is the probability that she has a birthday which is on a different day from the first guy? It's 365. Because, I mean, the other guy used one of the 366 days, so it's 365 over 366. It's nearly 1, but not quite 1. Okay, now you want to invite another guy. What is the probability that this birthday is different from?
364.
Yeah, it's 364 over 366. Okay, so this is first, second, third. Okay, now you want another lady to come in. What is the probability that she has a different birthday from everyone else? Well, there are 363 days left. So that's the fourth. And the probability that they're all different, since these are all independent events, is the product of all of them. Now, the nth guy comes along. Let's make it a man so that we don't discriminate. Okay, so what is the probability that the nth person has a birthday on a date which is none of those?
366 minus that. Minus that plus 1.
Okay, so it's 367 minus n. We can check whether this works. Okay, so for the first one, it would be 366 over 366. For the second one, it would be 365 over 366. For the third, 364 over 365, and so on. Okay, so the probability Pn that n guests that we have invited into the room V101 all have different birthdays based on our assumptions is this horrific product. So the probability that 2 of the persons have a birthday on the same day is 1 minus Pn. And we want this to be greater than a half. Now, I'm not asking you to solve this, but people have done this for us. It's sufficient to have 23 people, at least. So if you invite 23 people or more at your birthday party, then you have a good chance that 2 of them will have the same birthday. And in fact, if instead of 23 you pick 30, the probability becomes very large. In fact, unfortunately, I don't have a sufficiently large sample here in the room, because otherwise I don't think there are 23 people in the room right here, right now. But we could perhaps run this experiment given time. We can do it afterwards. So you can compare your birthdays, and it's not so unlikely the two of you will have a birthday on the same day. If the room was packed, as it should be, of course, then the probability would be incredibly high. Incredibly high. This sounds odd, doesn't it? But that's what probability is for. It gives you, of course, I mean, there are some slight tweaks here that have to do with the fact that the assumptions that we are making are not completely true to life, but they are sufficiently close to being true to life. But certainly they would disappear if we had 150 people in the room. Now you might say, okay, that's a game. What does this have to do with computer science? Well, let me give you a hint of why this type of mental masturbations actually do have something to do with computer science. Sorry, I should not have used the word masturbation here. But you're all grown up anyway, so I can do that. So let's look at something that I'm sure you have seen during the data structures course. And if you haven't, you will certainly see it during the algorithms course. Well, actually, I know you've seen hash tables in the data structures course. Now, what is a hash table? A hash table is a data structure, otherwise you would not see it in the data structures course. Silly Luca. But how does it work? Okay, it's used to store data items, but we want to refer to these data items using something that we call a key. This is a typical data structure for quick search. In fact, it's used very often to implement dictionary-type data structures. Okay, so how does this work? Well, each data item comes equipped with a unique key. And we want to use the key to store the data structure, so to store the data item in our data structure, and also to retrieve, to search for the data item using the key. And this is often done using a hash function. Now, what does a hash function do? It tells you where you should go about storing your data item with that key and where you're more likely to find it. Typically, a hash function is a function that goes from a large collection of keys to a typically smaller collection of memory locations. And the idea is that if you want to know where you should store a data item with key K, you compute the hash of the key, and this will tell you the memory location where you should put that data item. Now, where's the catch? The catch is that since the collection of keys is much bigger, typically, than the collection of memory locations, very often you have collisions. Collisions are a fact of life. Now, what is a collision? A collision occurs when you have two different keys that are mapped to the same memory location by the hash function. And this is bound to happen. Why? Because we got way more keys than memory locations. The function has to map a key to a memory location. Well, this can only happen if more than one key actually goes to the same memory location. And then we have ways of getting around this fact that you have collisions. Chaining and linear probing, whatever tools you have seen in the data structures course, or you will see in the algorithms course. Now, a natural question to ask yourself is, what is the probability, Pn, that there are no collisions when I insert n keys in my hash table using a function h? Well, you know what? This is actually the birthday problem in disguise. Why? What is the probability Pn that you don't have any collision? Well, now instead of your birthday room, you have your collection of memory locations. And now instead of your guests, the keys come along. Now the first key comes along. What is the probability that it lands in an occupied memory location? It's 0. So the probability that there is no collision is 1. But now, what is the probability that the second key causes no collision? Well, if it goes to in any of the m-1, assuming that you have m memory location, in any of the m-1 available free spaces. So the probability is m-1 over m. The probability that the next guy finds a free spot is m-2 over m, and so on. So the probability of Pn, of getting no collisions, is the product of all of these probabilities. So that's exactly the same as the birthday paradox, but now we are interested in Pn, the probability that no two guests have the same birth date, or no two keys are mapped to the same memory location. So what looks like a fascinating puzzle that you can use to entertain your guests at your birthday party is actually a problem in computer science. And in fact, it's an important problem in computer science because you want to typically to maximize this quantity that by selecting an appropriate hashing function. And if I remember correctly, but don't quote me, even though I'm going on YouTube live with my possibly wrong recollection, it was Donald Knuth who actually calculated these probabilities in the first place. Okay, so if somebody tells you, why should I care about the birthday paradox, you tell him, you know, it's about hash functions anyway. And hash functions are cool because they are a nice data structure that we use all over the place in computer science. Then if that person asks, why should I care about hash tables? Then you say, okay, you're not a computer scientist. Do something else with your life. Or join the computer science course and you will become like me. Like me means like you, not like me. Okay, so by now I think you know a fair amount about probability theory, so you can put your knowledge to good use. For instance, to impress people with your psychic skills, or to generate random numbers by using this fantastic random number generation routine from XKCD. I thought I should just entertain you before we move to a different topic, but there you are. I don't know whether you ever tried this trick to impress ladies or gals or guys you might be interested in. It doesn't often work, but when it does, it's totally worth it, as the guy says. And remember what I told you about Kolmogorov complexity as a Kolmogorov definition of when something is random? Something is random if, well, a bit sequence is random if the shortest program that can generate it is actually longer than the sequence. Well, if you throw a die, you get a 4. You may get a 4. That's random. But if you repeat 4, 4, 4, 4, 4, 4, that doesn't look particularly random to me. You can actually, the probability that you get it is very small, yes, but you can write a very short program to generate that sequence of 4s, repeat 4 forever, and you can get it for as long as you want. It's a very short program. It can generate a very, very long sequence of 4s. Okay. And since you are all very interested in cultural things, so here's another example of something that has to do with probability. I don't know whether you've ever read Pete Hines' Grooks. It's a bit of Danish culture for you. Here's an English translation, and I particularly like the one called A Psychological Tip which is over there, it basically says that whenever you don't know what to do when you're faced with a choice, you should use probability. You toss a coin, but not because you're supposed to follow whatever the coin tells you to do. It's because while the coin is actually floating in the air, all in a sudden you would know what you want. So that's not quite an application of probability theory, but it's a psychological tip. So if you want to know whether to go left or right, whatever left or right might be for you, next time you need to make a choice in life, toss a coin, and while it's flying in the air, you will know. You will know. And if you still don't know, well, then follow what the coin tells you. At least half of probability I have, you're doing it right, which is higher than what most of us actually get in real life anyway. Okay, sort of enough culture for people who are getting bored with cultural phenomena. By the way, I strongly recommend reading the Grooks, especially in the original, Danish. And since all of you read Danish, I believe that's possible. Otherwise, you can read them in English anyway. Okay, so the last new topic in the course that we are going to introduce now, and that we will wind up on Thursday. After which, it's only recap. So breathe a sigh of relief. We are going now to look at something which is called random variables and expectations. Now, this sounds like a very strange thing, perhaps, random variables, expectations. Well, it's not so strange, because you already know what random variables are, even though I have not used the word before. And expectation is actually something that you want to do in real life all the time. You very often want to calculate whether the odds of something happening are good for you or bad for you, so that you know how to make good decisions rationally. So what is a random variable? Well, a random variable is neither random nor a variable. What's for a good, well-chosen name? A random variable is actually a function. It comes from the English translation of the Italian variabile casuale, which really means random variable. So this is an Italian name, so it's no surprise that it doesn't have anything to do with randomness or variables. But anyway, so it was the Italian probabilists who introduced this. So suppose you have a sample space, and that's something that we've already seen. It's the collection of possible outcomes of a probabilistic experiment. Now, a random variable over this sample space is nothing but a function that associates to the possible outcomes a real number. Now, you can think of this real number as being some kind of payoff. So if something happens, you get, if S happens, where S is one of the possible outcomes, you get X of S paid. Here's an example. Suppose I have a die in my hand, and I want to play with you a game. And the game is as follows. I throw the die. If the number that comes out is odd, I give you as many kroner as the number of the die. So for instance, if the outcome is 3, I give you 3 kroner. If the outcome is even, you pay me that amount. So if the outcome is 2, you give me 2 kroner. Would you want to play this game with me over and over again? Your colleagues here are saying, no, God forbid. But why? Well, what I've just defined is a random variable. And once we have learned how to compute the expected value of that random variable, you will see that your colleagues in the room are actually right in not wanting to play the game with me.
Because either you pay 2 or 4 or 6, or you get 1 or 3 or 5, either way the average is
Absolutely. It's a question of averages. And the average is nothing but another way of computing. It's a weighted average, actually. It's another way of saying the expectation, the expected value, or also called the mean of this random variable. Now, what is the random variable here? Let's use the definition. So since random variables, we've been calling them X. Okay, so what is the sample space? I throw a die. So the sample space is the numbers from 1 to 6. And we said that the random variable should give a real number. In this case, it would be an integer, but a real number to each one of the outcomes. So here's what we get. If the number is odd, this will be, oh, sorry, it would be plus. I was turning the game on its head now. If the number is even, then the payoff is negative. Oh, sorry, 0 is not. It's not there because I'm starting at 1. So that's an example of a random variable. And it's the random variable that corresponds to the game that I was telling you before. The sample space is the possible outcomes of a die cast, and the payoff, X of a number, is what you pay me or what I pay you, depending on what the result of the die cast is. Okay, so this is not a mind-boggling concept. It's just a function. But it can be used. It's a very, very general concept because it can be used to express many different scenarios. So let's look at a few more of those. So the value of a die cast, of course, this is an example of a random variable. In this case, the payoff is exactly what you see. It's the value of the die cast. So if I get a 3, the value is 3. The sum of the values of 2 die casts is also a random variable. In this case, what is the sample space? Okay, so the sample space corresponds to pairs of numbers between 1 and 6, all possible pairs of numbers between 1 and 6, and the outcome is the sum of the component of the pair. So for instance, X of 1, 3 would be 4. Because I'm interested in the sum of the values of the 2 die casts. It's very useful if you're playing Monopoly, as I need to do quite a bit these days. Or the number of heads in 3 tosses of a fair coin. Okay, in this case, the sample space is strings of heads and tails of leg 3, and X of head, head, tail would be 2. The last one is more interesting. Okay, so suppose I take a fair coin and I toss it. What I'm interested is in the number of tosses of the coin I need to make before a head comes up. Okay, so in this case, the sample space is sequences of heads and tails, arbitrarily long, any finite amount. And the value of a sequence is the number of tosses before the first head. So if I have tail, 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 head, and then something else, that would be tail, 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 head. So it's 4. Okay? Now, of course, since we are tossing a fair coin, we expect that the probability of a very, very long sequence of tails slowly decreases to basically 0. So you would expect, but in principle, you can, with very low probability, keep tossing and getting tails all the time. But only getting tails forever, that's a probability 0 event. It gets close to 0 very, very quickly. Now, a question that we can ask ourselves is, what is the average number that we can expect from a die cast? Okay, I know I can get any of the numbers from 1 to 6, but what is the average number that you expect? Okay, one of your colleagues is saying 3.5, and that's the right answer. But how do we calculate this? Or, for the example of the game that we were playing before, what is the average payoff that you would expect to get? How much? So one of your colleagues is saying?
3.
For this game?
Like 3 for payoff, 4 for loss.
Okay, so he's saying 3 for, let's see. Let's see what happens. So how would we calculate what is the expected average gain, if anything, for you in this game? Okay, so I'm throwing a die, and there are 6 possible outcomes. Now, we can assume that the die is not, well, is fair. So each one of the possible outcomes is equally likely. So I can get a 1 with probability 1/6. But if I get a 1, I pay you. So you gain 1. But we can also get a 2 with probability 1/6. But in that case, you pay me. So for you, it's a loss. Okay, we can also get a 3 with probability 1/6, in which case you get 3 kroner from me. We can get a 4 with probability 1/6, but then you pay me. We can get a 5 with probability 1/6. I pay you. Or we can get a 6 with probability 1/6, but then you pay me. So somehow, the expected payoff for you guys, or for me for what matters, but I'm focusing on you, is the value of this apparently complicated expression. Now, but what is this? I can take the 1/6 outside, so it's 1 minus 2 plus 3 minus 4 plus 5 minus 6. Now, what is this? Okay, so let's focus on the pluses. I put them in green because they are good. Well, they're good for you. So it's 1 plus 3 plus 5. Yeah, so this is 9, isn't it? And but there's also minus 12. So if I look at the reds, now I'll put this in red because it's the dangerous stuff for you. That's minus 12. So we have minus 12 plus 9 divided by 6, which is minus a half. Because it's minus 3 over 6. So every time we play this game, you're likely to give me 50 euro if we were in Denmark. Okay, so if I play this game repeatedly with you, and I play sufficiently long, where sufficiently long would be a lot of trials, I stand to gain from playing it. So that's the reason why your colleagues from the very beginning said, we are not going to play this game with you, Luca. No way. Even though we are talking about very small amounts of money. Because we have a higher likelihood of losing. This value here, minus 0.5 or minus a half, is actually the expected value of this game. The expectation of the random variable x defined in this way. And as your colleague said before, the expected value that you get from a random diecast is 3.5. What we are going to see on Thursday is what is the formula for calculating the expectation. And this formula for this specific game will give you exactly what we calculated. And what kind of properties expectation has, and how these properties can help us compute the expectation for apparently rather complicated scenarios and random variables. And after we've done that, we have covered all of the topics in the course. Any question?
Is the test we need to finish by the end of this week the last delivery?
The question is the test we need to finish by the end of the week the last one to deliver? The answer is yes. And there was great rejoicing. Okay? Vi ses på torsdag.